x such that so that thing I'm going to call pi. Pi is actually pi high of okay, so let me pi high of summation pi pi I. Okay, so this is the one object. It's a projection matrix for every x. Apply that thing on f of x. F of x is a vector field. And if this is 0, then you declare yourself to be on the manifold. If it's not 0, then you declare yourself not to be on the manifold. Okay, so this is the scheme. And this scheme is claimed to be giving good answers. So that's the main theorem. So this is about getting the curvature right. I'll skip this. But this is, so this pi x of f of x equal to 0 is, this is pi x, it depends on x, and this is f of x equal to 0. This is how you define the manifold. You can verify membership, but I think the more useful thing would be to get a projection onto the manifold by following the vector field or something like the subspace constraint vector field, because it's a low dimensional manifold. You're never going to be exactly on it. Yeah. So I mean, this is the solution of a well-conditioned set of equations. And you can, from given a point, you can trace the vector field and get to the point which is 0. It won't be too far from the projection of the point from the set. So if you just look at this, right, and you try to minimize the norm squared of this, and you'll do some gradient descent, for example. So that would be a natural way to do it. I won't make any strong claims, but this is one way of getting a reasonable nearby point. If you start sufficiently close by, it's like a Newton method, you get to a 0 that is really. No, it won't have any spurious things, because so what this what is, so locally this is looking pretty much like what happens with the ball, right? In the ball, it's basically the gradient of the squared distance. This thing is the gradient of the squared distance from the disk. So it's if you want this to be 0, it's not like you're going to find a 0 somewhere here or here. You will have to go here, because this is pretty much an identical copy translated. So that is actually proven that the reach of the resulting set is tau by d raised to 7, and that comes from local considerations. It doesn't come from the global things are far off. Yeah, at least tau off, because that's you're approximating a manifold that has that much reach. So how does one actually get the local computations? One has to use the implicit function theorem to say that, okay, this is a solution of some equation, and one has to bound the second derivative of the solution, and yeah, so we used a quantitative implicit function theorem that has no dimension dependence. And so this is the form. It basically says that if the Jacobian is close to identity in some restricted subspace, I guess, then and the second derivative is small, then the 0 set of the equations is going to look pretty flat, and it's going to give you a manifold that is good. So technical. So this is basically the theorem at the end of it. So we say that suppose some conditions are true for the noise, then the reach of the manifold is greater than tau by d raised to 7, and the distance between the output manifold M0 and M is less or equal to something that is like sigma squared, not sigma. Sigma squared improvement was obtained by doing that averaging. So I told you that, you know, here there was this. I took the nearest projection matrix to a semi-definite positive definite matrix. So that actually comes from some rather, I find, magical complex analysis. So this is complex analysis over matrices. If this is a diagonal matrix, this is Cauchy's integral formula applied entry-wise on each of the diagonals. But you can diagonalize positive definite matrices, and so this becomes true for all cases. So it's basically a a closed form, and this is if you want to differentiate pi x as a function of x, because this description is not explicit enough for that. So, I just conclude that we get a small Hausdorff distance and good reach, and the computational complexity depend only on the intrinsic dimension. Thank you. I have not, no. I see. Yeah. Mhm. Yeah, I'll contact him. Thank you. Thank you.